Good afternoon, everybody. Welcome to Sunny Afternoon of Organic Chemistry, Chem 170, with your host, me, Dr. White. Hopefully you're ready for an exciting afternoon. First of all, I'd like to thank all of you except one who hasn't done it. Hopefully you'll get it soon for handing in your lab. I'll be grading labs later this afternoon. Also, if I looks like I've been a little harried and like on the rush, I have, because this morning, the other school I teach at College of DuPage, I had our first lecture this morning. I taught from 9 until noon. So today's a busy day for me. Let's see if I'll wilt away or do I have the strength to continue on? I do. All right, couple things. First of all, sometime, I don't know when I had time today, if you look in the assignment area, you can download the lab we're doing tomorrow. And tomorrow, Wednesday, we'll be doing a lab. The lab we did on Monday is due tomorrow. I'll say that again. The lab we did on Monday is due tomorrow. Make sure you get your labs in on time. And I will put out an email to remind you. I think that helps. And as you notice, I've been keeping up with our lectures on our YouTube channel. With that, let's get back to work. We've been talking about aromatic compounds. Anybody happen to smell any vanilla or cinnamon? You're smelling an aromatic compound. That's organic chemistry. I got asked, anybody drive by a gas station and think about half the way to the gas station is alkanes? Or do you happen to look at a candle and half the way to the candle is alkanes? Did you look at a container of Vaseline, otherwise known as petroleum jelly? That's alkanes. And also baby oil, that's alkanes. Remember, when you leave my lecture, look all around you because organic chemistry is all around you. I stole that from SpongeBob. And you should think about it. It won't hurt. Trust me, I'm a doctor. Does that work? Trust me, I'm an organic chemist. Oh, that worked. Think about it. It won't hurt. All right. Now, we were going through nomenclature. When we finished that up, remember we talked about ortho, meta, and para, which is ortho is 1,2-disubstituted, meta is 1,3-disubstituted, and para is 1,4. Uh-oh. I was so excited to get into that. Bad, Dr. White. Shame on me. I forgot, I promised, we should go through the problem set. So I better open it up. That happens once in a while. I forget. That I promised I'd go through the problem set. Bad, Dr. White. Does everybody know what that means? I had a student who was from China and she didn't. Well, she grew up in a different culture. And I taught her that and also what that meant. You're crazy. In case I was saying I'm crazy. Sometimes I am. All right, thumbs up, people. Since nobody has their monitor on, use the emoji. Does everybody see alkenes problem set? Thank you, thumbs up, people. All right, let's take a look at this. Now, remember, if you have a question, ask. There's no such thing as a dumb question in my class ever. Now, first problem is give the IUPAC name for the following. And here, what does IUPAC mean? The official name. So when you look at a molecule, look for what's different. What's not a carbon-carbon single bond, carbon or hydrogen atom, ooh, a double bond. And that's an alkene. How do we name that? Name the number of carbons in the longest chain that has both carbons of the carbons of double bond. 4, butane. Drop the A in the ending, put E on E. butene. Next, if it's which carbon of the two carbons double bond is closest to the end of the chain, and give that a number as if you were counting it, the chain for alkyl groups. In this case, it's 1. Now, if you have two of the same atom or carbon on the same carbon of the double bond, you can't have cis trans isomerism, and we're done, 1-butene. Now, let's skip to C, and we'll come back to B in a second. And here, ooh, double bond. Now I'm showing stereochemistry. The longest chain is 1, 2, 3, 4, 5. Pentane. But we have a double bond, drop the A and E, put in ENE, pentene. And now, what carbon is closest to the other double bond carbons to the end of the chain? This is 1, this is 2. Went the other way, this would be 1, 2, 3. 2, I hope you agree, is lower than 3. So this is 2-pentene. Now notice each carbon of the double bond has a hydrogen. And if I were, and unfortunately I'm on a PDF, if I drew a line this way, or put my finger over that, are the two hydrogens below that line on the same side or on opposite? And the answer is same side, and we call that cis. So this would be cis-2-pentene. Hang in there while I had my tablet off. I'm thinking, oh no, it's broken. No, you turned it off. Now I turned it on. And why don't you give the IUPAC? And I'm going to share the fun. Your turn. Give the IUPAC name for the following molecule. 3 points each. And when you're done, give me a thumbs up emoji, or as I like to call them now, symboli. I don't think that's going to catch on. And for those who are not done yet, for those who are done, please be patient. I try and give everybody a chance to finish. All right, I think everybody's done. If not, give me a thumbs down or make noise. Well, I guess everybody's. So look at this molecule, determine how to name it, and what's different, a double bond. How many carbons in the longest chain with both carbons of the double bond? And the answer is 6. And hopefully by now, hopefully, hint, hint, you've learned the alkane name, and 6 is hexane. But it's a double bond, so you drop the A and E and put hexene. Next, what carbon is the lead carbon? This way is 2. We want the other way to be 1, 2, 3, 4, which is smaller, 2 or 4. Time's up. Hope we all pick 2. Are we done? No. If I had a plane, which I'm drawing in, or your pencil or your finger there, notice this hydrogen and this hydrogen are on opposite sides. Cis is the same, trans opposite. So that would be trans 2-hexene. And that's how you do it. Let's go back to the problem set. Now, if we look at B, I don't know what that was. If we look at B, we have right now a ring, and it's got a double bond. And how many carbons in that ring? 6. Hexane. It's a ring cyclohexane. And you drop the A and E because it's a double bond cyclohexene. And now in a ring, when it's the only functional group, and that's going to be the case in this course, one of the carbons of double bond has to be 1, the other has to be 2. And if I number this 1, this 2, and you number it in such a way that all the substituents get the lowest numbers. And, excuse me, if the methyl group is on 1 on the ring, the ethyl group is on 3. So it'd be 3 ethyl, 1 methyl. Since I'm not holding you to the alphabetical rule, if you put down 1 methyl, 3 ethyl cyclohexene, you would be correct, even though you packed this the correct way. And this is an important thing. And this is 1, this has to be 2, that's 3. Now, let me just point out something that you wouldn't do, but students make a mistake and they say, why don't I make that 1? And that would be 3. Well, these 2 carbons have to be 1 and 2. So if I call this one 1, this has to be 2, 3, 4, 5, 6. And then the ethyl group would be on 6 and the methyl on 2. And those are larger numbers than 1 and 3. That's why the way I did is the way I did it, which is the correct IUPAC way. Now, D I had there, if you have 2 of the same group on a carbon double bond, you can't have cis or trans. Notice I have 2 CH3 groups, even though 1 is included in the longest chain. When you're doing cis and trans, that's considered 2 of the same group. And therefore, 1, 2, 3, 4, 5 carbons, pentane, double bond, pentene. The lead carbon is on 2 pentene, and there's also a methyl group there. And that's why there's no cis or trans. Now, there are 2 types of nomenclature questions or skills you should have in organic chemistry. One is, here's the compound, give the IUPAC name. The other is, here's the name, draw the structure. And notice I have here cyclohexene, start at the right, ENE ending tells you double bond. And if we're ANE, cyclohexane, 6-membered ring, and it's one with a double bond. Now I wrote it there, but since a ring can rotate, it's not glued to the paper. You could have just easily have done this. Whoops, not in red though. This would be an example. All I'm doing is rotating the ring. You could have it here or between any 2 carbons on that ring, and they'd all be cyclohexene. Now, if we look at C, 5,6-dimethyl trans 3-octene, how do you decode this to determine what to draw? Well, first of all, ENE ending, you start from the right, move left. Octene, ENE double bond, if there were 8 octane, 8 carbons, 1, 2, 3, 4, 5, 6, 7, 8. Now, there's a double bond. What's the lead carbon of the double bond? carbon 3. So between 3 and 4, I have my double bond. Notice it's trans. The hydrogens are opposite, and so are these chains. And on carbon methyl, you know CH3, di means 2, and they're on carbons 5 and 6. And if we look at D, 3-isopropyl 2-tert-butyl cyclopentene, we start from the right, ENE ending, double bond. If that were ANE, that'd be cyclopentane, a 5-carbon ring. It's got a double bond. One of the carbons is going to be 1. Then on carbon 2 is a tert-butyl or T-butyl. And the dreaded hydrogen virus got this PDF. On that carbon, there should be a hydrogen. Don't look, it's missing a hydrogen. Oh no. Anyways, isopropyl group. Now, one of the things a couple of years ago, students were asking me, and I said, well, you don't really know, but they got all upset and they said, we want to know how to use the full line method like you'd see on the internet. And when I have a ring, I'll do that. And this is a T-butyl group. This is isopropyl. You can do either one on the test, but this one I think will be easier for you. All right. Now, coming up soon, not that far away, is test number 1. And test number 1, there are 3 types of questions I can ask. One is general knowledge. What would be general knowledge? How many bonds to carbon are there? You're right, 4. Remember, that's your friend. The other thing is nomenclature. 2 types of nomenclature. That is, here's the name, here's the structure, give the IUPAC name, and here's the name, draw the structure. And the third type is reactions, and that's the fun part of organic chemistry. But then again, I'm a synthetic organic chemist, and I've been trained to use those reactions to make things, which is the real fun part. So let's continue on. And number 3, give the organic product or products. The S is in the bracket, meaning sometime in the future there might be more than one product. And for the following chemical reactions. And if we look at this, A, what do we have? This molecule reacting with hydrogen and nickel catalyst. And when you look at a molecule, look for what's different, look for the functional group, otherwise known as what's not a carbon-carbon single bond, carbon or hydrogen, a double bond. Reacting with hydrogen and a catalyst. I should have put down the catalyst can be nickel, platinum, or palladium. And you break the pi bond. Remember, double bonds, 1 pi bond, 1 sigma bond, and each carbon of the double bond gets a hydrogen. Do you break carbon-carbon single bonds? No. So I started out with 4 carbons. I ended up. Now, if you had a hydrogen pointing down here and here, that would be fine. And here's one for you to have some fun with. What would be the organic product or product for the following? And since all of you have your web camera off, I don't know, does Jewish guilt work? No. But anyways, don't forget to use these emoji, thumbs up, or the party horn, or whatever one you want to use, to let me know when you're done. I think everybody's done. Isn't Dr. White nice? He shares the fun. And now we'll look at this molecule. What's different? What's not a carbon-carbon single bond? Carbon hydrogen? Oh, look, a double bond. What are we reacting with? Hydrogen, gas, H2. What's palladium? A catalyst. And the catalyst can be palladium, platinum, or nickel. And you break the pi bond, not the sigma or single bond, and each carbon gets a hydrogen. Now, how many carbons we have? 1, 2, 3, 4, 5 across, plus a methyl. 1, 2, 3, 4, 5. And I have that methyl group. Here are my 2 carbons with double bond. Notice I broke the pi bond, and each one, like my general reaction, gets a hydrogen. Then I know there are 4 bonds to carbon. And I can put in my hydrogens. And remember, it's your solemn responsibility that if I make a mistake putting in hydrogens, let me know so I can correct it. And that's how you do it. Now, if we move on to the next group of problems, we have C and D. What's different? A double bond. And here in C, and D is the same thing, just a scary molecule. If you don't know, look for the functional group, and then it's no longer scary. Double bond reacting with chlorine, gas, Cl2, that's a halogen. You break the pi bond, each carbon gets a halogen. By the way, X can be fluorine, chlorine, bromine, or iodine. In this case, 3 carbons, 3 carbons. Here are the 2 carbons, double bond. Here are those 2 carbons. Break the pi bond. Each carbon gets a halogen, chlorine. And same thing with bromine. Now, let's look at G. Again, what's different? I'm about to sneeze. Hold on. Oh, excuse me. A slow developing sneeze. Anyways, we look at E, we're reacting what? A double bond, look for what's different, with HBr. Halogens are X, HX. And X can be, in this case, chlorine, bromine, or iodine. And you break the pi bond, 1 carbon gets H, the other gets X, and it follows Markovnikov's rule. The carbon with the most hydrogens gets the hydrogen, the other carbon gets the halogen of the double bond that you break the pi bond. And the other way of thinking of it is rich get richer, poor get poorer. We're talking about hydrogens, not money. So if we look at the 2 carbons double bond, this has 2, this has 1, which is greater. Hope we all pick 2. So the hydrogen goes to the end carbon, and this carbon right here gets the halogen. Now, if we look at F, oh no, it's a ring, and students do not like rings. Mother Nature and Dr. White love rings. Let's take a look at this one. I just forgot what I reacted with, so I'm going to sneak a peek. HI. And if we look at the ring, we got a ring, but oh, look, a double bond reacting with hydrogen iodide. And that's a halogen. Remember, X can be chlorine, bromine, or iodine. And you break the pi bond. Remember, there's one pi bond and one sigma bond. And each molecule carbon of the double bond, one gets H, the other gets the X, and it follows Markovnikov's rule. The carbon of the double bond with the most hydrogens gets the hydrogen, and the other one gets the halogen. Oh no, it's a ring. I don't see any hydrogens. There are, if you know, there's 4 bonds to carbon. We look at this carbon, how many bonds are there? 1, 2, 3. 4 minus 3 means there's 1 hydrogen on there. You don't show it, but there is. Now, if we look at this carbon right here, there's 1, 2, 3, 4. 4 minus 4, so there's 4 bonds to carbon, is 0. A little bit of 0. And the question is, which is the larger number? And that carbon right there. So you break carbon, carbon, single bonds. No. So I'm going to still have my isopropyl there. I'll still have my methyl group. Now, if you notice, I broke the pi bond, and this carbon has less hydrogen, so it's going to get the halogen. In this case, it's iodine, and you don't show the hydrogen there, but there are now 2 there, 4 minus 2. Now, if you had written the methyl group where the iodine is, the iodine where the methyl group is, that's fine. Now, if we look at, let's do I. What do we have? We have a double bond. H plus is acid catalyst and water. If you look up at the top here, I have this general equation, double bond, which we have here, reacting with acid and water, acid catalyst H plus, water, think of it as HOH. You break the pi bond, one carbon gets H from the water, the other gets OH, the hydroxyl group, and it follows Markovnikov's rule. The carbon with the most hydrogens gets the hydrogen from water, and the other gets OH, the hydroxyl. So if we look at this example in I, the carbon here at the end in the double bond has 2 hydrogens, and the other carbon has 0, which is the higher number, and hopefully you pick 2. Now you have 1, 2, 3, 4, 5 across. You have 5 across. Oh no, don't look. The hydrogen virus got me again. That should be CH3 down there. Sorry. But anyways, this carbon at the end gets the hydrogen, and the other carbon, as per this reaction, gets the hydroxyl group. And other than the fact that those hydrogens fell off, this is correct. Next, let's talk about triple bonds. I should mention that, remember, there's no such thing as a dumb question. If you have any questions, always feel free to stop me and ask them. All right, now, it says give the IUPAC name, not common name. Now, this first one is the simplest alkyne, a triple bond. And name the number, count the number of carbons in the longest chain that contain both carbons of the triple bond. Name it as an alkane, drop the A on the ending, put Y on E. And this would be ethine. Now, this does have the common name acetylane, but remember, I'm asking for the IUPAC name. And if we look at C, what's different? What's not a carbon-carbon single bond, or atoms that are not carbon or hydrogen elements have a triple bond. How many carbons along this chain? 1, 2, 3, 4, 5, 6, 7. That's heptane, alkane. But for a triple bond, alkyne, you drop the A in the ending, put Y in E, and then you need which carbon is close to the end of the chain while also giving the alkyl groups low numbers. And if you start here, 1, 2, 3 is 3-heptine. And then, oh, it's your old friend, the methyl group CH3 on carbon 2. And that's how you do that. You don't have to raise your hand or anything, but I wonder how many of you saw a T-butyl group. Wrong. Longest chain is 1, 2, 3, 4, 5, 6. Hexane, it's a triple bond right here, hexine. And then on carbon 3, 1, 2, 3, it's the lead carbon, triple bond. Now you go from the side that gives the lowest number, but also at the same time give the alkyl groups the lowest number, which I didn't start from this side. So it's 3-hexine, and then we have 1, 2 methyl groups, di meaning 2, remember tri is 3, dimethyl, and they're both on the same carbon, 2, 2. When they're on the same carbon, don't put just one number. Di tells me I need 2 numbers, and that's why I have 2, 2. Now, one of the things I'll be doing throughout the semester, I will never ask you what's the common name of a compound, but I will ask you draw the structure given the common name. Why? Because that's where you're going to see them on ingredients labels. I have yet to see something I buy in a store that has the structure on it in the ingredients label. You see something, let me know. All right, acetylane is the only, for these chapters on alkenes, alkynes, I asked you to learn the structure of this common name. And that's this triple bond, the simplest alkyne, 2 carbon triple bond, each carbon has hydrogen. This hydrogen is left justified. You could have put it also to the right of the first carbon. We look at 2,5-dimethyl 3-heptine, start from this end, and YNE ending, triple bond. Now we're ANE, heptane, which is 7, so I have 7 carbons across, 5 plus 2 more. Then carbons 2 and 5 are dimethyl, di2, methyl, CH3, carbon 2 methyl, carbon 5 methyl, and there you go. You know what I forgot to do in this problem, part of the problem set? Here's the name of a structure. Oh, no, wait, I have this. Did I have? Ah, I lost my train of thought big time. Sorry. All right, and the third type of question on test number 1, 2, or 3, or 4, the final, is reactions. And here, if we look at B, what's different? Ooh, a triple bond. What are we reacting with? Hydrogen and the bracket X, letter S, close bracket, means you have all the hydrogen in the world with anything hydrogen we're going to react with. That way we don't have to balance it because we're lazy organic chemists. And here, hydrogen, what do we have? I forgot to put the catalyst there when I wrote that. I put it on the answer sheet. Platinum, which is a catalyst. You break not 1, but 2 pi bonds, and that's what you get. Each carbon of the triple bond gets 2 hydrogens. Do you break carbon-carbon single bonds? No. So I have 1, 2, 3, 4, 5, 6 across, 6 across. This carbon has 2 methyl groups. It still has 2 methyl groups. Each carbon of the triple bond, notice I wrote 2 pi bonds, gets 2 hydrogens. And with halogenation, the same thing happens. You have a triple bond in this one, excess halogen, in this case bromine. In this case, X can be chlorine, bromine, fluorine, or iodine. And the 2 pi bonds are broken, not the single bond. And each carbon of the triple bond gets 2 halogens, 3 carbons, 3 carbons. Here are my 2 carbons of the triple bond. Each one gets 2 halogens. Total of 4. Same thing here, except here's the triple bond, and everything else comes along for the ride. And that's problem set on alkenes and alkynes. But what I didn't have there, and you could do any one of those problems on your own, make it into a synthesis problem. On test 1, I'm going to have only one synthesis that can be for any general reaction. But let's try one. That happened. Everybody hear me now? Okay. The question is, what would be the starting material used to make that molecule? 3 points each. Your turn. And when you're done, give me a thumbs up. All right, I think everybody's done. So let's have fun and do it. If I look at the product here, what's not a carbon-carbon single bond or not a carbon or hydrogen atom? Oh, look, 1, no, 2 iodines, which are halogens, and they're on adjacent carbons. Adjacent means connect to each other, next to each other. And I'm reacting whatever I'm starting with halogen gas. Remember, X can be fluorine, chlorine, bromine, or iodine. And what do we start with? A double bond. And remember, the 2 carbons with the halogens are the 2 carbons of the double bond. So you notice I'm not adding any carbons, so I end up with 2, 3, 4, 5. I better start out with 1, 2, 3, 4, 5. Which carbons have the halogens? These 2, which are these 2, which means those are 2 carbons in a double bond. Let me clean this up. And now I know there are 4 bonds to carbon, so I can put in my hydrogens. And if you take this molecule, it will give you that product. Oh, this is fun. Let's do one more. And why don't you try this one? What would be the starting material that I react with acid catalyst and water to make that molecule? 3 points each. Or maybe this one might even be 4. Just a little more challenging. Let's see, one person's done. Let me go looking. All right, everybody, real quick, if you're done, give me a thumbs up. Or I could also do this. Well, I think everybody's done. And how do we do this? Well, you look at the product and say, what's different? Ooh, what's not carbon? What's not hydrogen? What's not a carbon-carbon single bond? Oxygen. And you have a carbon with a hydroxyl group and an adjacent carbon with a hydrogen. And you do in the ring. And what do you react with acid and water to make that? A double bond. Remember, it follows Markov-Nikols's rule. Now, what does this tell you? You have a carbon with a hydroxyl group, an adjacent carbon, and those are the 2 carbons that double bond. So this carbon right here has to be in the double bond. Am I adding carbons? No. So it still has my 2 methyls here. And this carbon has to be in the double bond. Well, where are the adjacent carbons? Here and here. Well, the molecule I have written, the only place you can put a double bond is there. Why not the other place? And I forgot my methyl group. Bad, Dr. White. I'm going to do this one in red because it's wrong. Why can't this be correct? Why is that wrong? Because we look at this carbon, how many bonds? 1, 2, 3, 4, 5. No way, you can't have 5 bonds to carbon. And if we come here, I'll put, this has 1 hydrogen, this has 2. And if you think of water as H, which I didn't have here, HOH, the hydroxyl group will go there and the hydrogen will go there, and that's how you do it. Oh, let's do one more. I'm having a good time. I hope you are too. And here you go. What would be the product or products for the following reaction? All right, I think everybody's done. Let's take a look. How do you do this? And if I look here, what's different? Oh, a double bond. Wait a second, double bond. And notice they're separated by more than 0 carbons. They're not connected together. So this is a unconjugated or non-conjugated double bond. I think it's non-conjugated. And so each double bond reacts like it's alone. What's chlorine? Halogen. Now the excess is because we have 2 double bonds and you need twice as much chlorine, but I don't want to balance the chemical equation. I am a lazy organic chemist, so this just tells me I have enough chlorine to react whatever chlorine will react with. Remember, X can be fluorine, chlorine, bromine, or iodine. And remember, this has 1 pi bond and 1 sigma bond, single bond. Break the pi bond, each carbon gets a halogen. Now, do you break carbon-carbon single bonds? No. So we have 1, 2, 3, 4, 5, 6 across. 1, 2, 3, 4, 5, 6 across. We look at this double bond. You break it, and each one gets a halogen, in this case chlorine. If we look at this double bond, you break the pi bond, and each carbon gets a halogen, and it's chlorine again. And I know there are 4 bonds to carbon, and halogen counts as 1. And I can put in the hydrogens. That's the 2. And that's how you do it. Does anybody have any questions? Guess what time it is? Time for a break. I'm going to take a 5-minute break. I'll see you back at 1:56. I went a whole minute over. Sorry. So come back in 5 minutes.
Until even the smallest detail.
Time to get going again. Welcome back. All right. Any questions on alkenes or alkynes before I continue? I guess not. Remember, always feel free to ask questions in my class or come to my office hours on Monday and Wednesday evenings. If you can't make it then, email me and I'll set up something special if you need help. All right, we're talking about aromatic compounds. And example would be benzene. Thumbs up, people. Can you all see benzene on the screen now? Thank you. All right, benzene. And don't forget to put double bonds or a circle inside. If I ask draw the structure of benzene and you do this, that's wrong. Without the double bonds, this is cyclohexane. And these two molecules are as different as your hands and feet or whatever other big night and day, you name it. And so make sure you put either that, the bonds, or another way, which I don't like to use, but if you want to go right ahead, you can put a circle in there too. Either way works. Now, same thing with toluene, methyl group on a benzene ring. Don't forget to put that. I won't ask about styrene. Now, we went through the nomenclature. Don't forget, you should now know from this list, chlorine is chlorine Cl on a benzene ring, or other things is a chloral group. Br, bromo, iodine, iodo, fluorine, fluoro, nitro, NO2, nitro. And sulfonic acid, I'll never ask on a test, but we'll talk about it later on when we talk about laundry detergent. Yep, I'll get into that in this class. Now, let's talk about the chemistry of benzene and aromatic compounds in general. Now, there's something called resonance energy. And can I have everybody's attention? Click the switch. Will this be on? A test is in the off position, but this is still important background information to understand the chemistry of benzene and aromatic compounds. Now, you got double bonds in benzene, and you think, oh, it's not that hard to hydrogenate it. Turns out it's very hard, much harder than to hydrogenate, say, a single double bond in a six-membered ring, a cycloalkene. Now, it does not react if it were considered three separate double bonds. Something is different. Benzene undergoes different chemistry, and same thing for other aromatic compounds. And what is that difference? It's called stabilization, or I like to name resonance energy. And that's the difference. Switches off, click. Will this be on a test? No, but it's good background information. And that is the difference between the energy of a real molecule and the calculated energy of the most stable conservative structure. So if you were to look at benzene and calculate, well, it's got a ring and three double bonds, it has a certain energy. And then if you were to measure, here's what you think it should be based on the energy of three separate double bonds in a ring, should be right here. If you actually measure it, it's much lower, lower being less energy, more stable. Again, switches off, but still, it's less energy. Less energy means more stable. It likes to be there. It's happy. Bet you didn't know molecules could be happy or sad, mainly happy. And this difference in the calculated versus the actual is called resonance energy. And that's caused by, let's go back, hopefully we're not getting dizzy now. The double bonds are formed by all the p orbitals forming these pi cloud where they're holding hands together in a circle. And they don't want to break hands because they're nice and happy and stable. So what does that mean? It means the chemistry of benzene aromatic compounds is called electrophilic aromatic substitution. And this is due to the resonance stabilization of the double bonds holding hands. They don't undergo addition reactions. It's really hard to make them do that, but they do substitution. If we look at benzene, I'll only do one carbon, but each carbon on this ring has one hydrogen. And the reactions of benzene and aromatic compounds, you replace that hydrogen with something else. Did I tell you you're going to learn a lot of neat words in my class that you can impress your friends, neighbors, and loved ones? Now that we're almost, hopefully we're done soon, at least in Illinois with COVID, but still, I'm wearing a mask when I go out. In fact, I don't know if I showed you this. If I can find them. Ah, here they are. One of the instructors at the other school who's good at sewing made me 2 chemistry masks. Everybody see the fancy chemistry stuff? And the other one is the periodic table. But anyways, make sure you're safe when you go out. But you'll be able to impress your friends, neighbors, and loved ones with a lot of new vocabulary. Now, electrophilic, what does that mean? Well, philic comes from the word phile, and that means loving. Like I'm an audiophile. That means I love music, and I have, let me count, 1, 2, 3, 4. I have 5 stereo systems in my house, and a couple of them are really good. There's even one in my garage when I'm working out there. I love music, so I'm an audiophile. Did I tell you my claim to fame is when I was a senior in high school here in Chicagoland, I saw Jimi Hendrix play live, the only time he ever had a concert in Chicago. The greatest concert I ever was in. And I saw Jefferson Airplane and a few other really good groups like the Moody Blues and all that. Now I'm showing my age, but Jimi Hendrix, if you don't know who Jimi Hendrix is, go to YouTube, look up Fire or Voodoo Mountain, or there are a lot of others. Purple Haze. He's probably the finest rock guitarist who ever lived. His death was such a tragedy. Drug overdose, unfortunately. But anyways, back to this, we have electrophilic. Phile is lover, electron, negative. So that's something that loves negative charge and deals with an aromatic ring. And substitution, you replace the hydrogen with something. Now, if we look at the ring here, what do you see up and above and below? The electrons from the pi cloud. So if I'm an electron loving whatever, it's called an electrophile. I'm looking for, ooh, where's their electrons? I see that aromatic ring, and boy, do I get attracted to that. And what that means is aromatic compounds undergo substitution. You replace one of the hydrogens with something, and there are chemical reactions where a hydrogen atom on the aromatic ring is substituted with an atom or another group of atoms. So what does that lead to? The first reaction of the electrophilic aromatic substitution reactions. And the first one is halogenation. Now, unlike with a double bond, you need a catalyst. And that catalyst is ferric trihalide. And for this reaction, I've only ever seen it done for chlorine or bromine. And therefore, I'm not going to do something that's not real world. So if you take a benzene ring, react it with a halogen plus that catalyst, you replace one of the hydrogens with the halogen, the other halogen plus the hydrogen form HX. Now, on a test, I ask give the organic product or products. HX is inorganic. You don't have to give it if you don't want to. So, benzene ring, halogen, catalyst, replace one of the hydrogens, doesn't matter on which carbon, with a halogen. And the question would be, give the organic product or products for the following reaction. And what do we see that's different? Ooh, a benzene ring. What are we reacting with? Chlorine, that's a halogen. And notice right here, you have ferric trichloride, a catalyst. And X here can be chlorine or bromine. And what happens? You replace one of the hydrogens with a halogen. In this case, what's the halogen? Chlorine. So the product I get is that molecule. Don't forget to put in the double bonds or circle. Otherwise, that's cyclohexane ring and it'll be wrong. And that's how you do it. I'm going to let you have fun with one too. And that's your chance to have some fun. Give the organic product or products to the following. I see the thumbs up are starting to pop up. If you haven't finished, take your time. I'll give you time to finish. Finish. I think everybody's finished. So what do? Well, we look at the reaction and say, what's different? Ooh, a benzene ring. What I'm reacting with, bromine is a halogen gas and ferric trihalide catalyst. Remember, X can be chlorine, or in this case, bromine. And what happens? You replace one of the carbons, one of the hydrogens on the benzene ring with a halogen. And remember, you should show the double bonds or circle, otherwise that's cyclohexane. So here's my benzene ring. I put in my double bonds. What's the halogen X? Bromine. I'm done. Now, notice both of these reactions, I started with nothing on the benzene ring. Each hydrogen is identical, so I can replace any one. What happens? All right, first of all, click whatever I'm going to talk about now. In the next couple minutes, I'm turning the switch. Will this be on a test to the off position? That's why I went click. Now, what happens if you have something already on the ring? And organic chemists for aromatic compounds, someone picked the letter Z. Don't ask me why, but they did. And what if I were halogenating it, just for an example? Well, one of these hydrogens I would replace. Well, it matters now, because if I replace either this one or this one, remember, switch is off, I'd get this. And if I replace this one, I would get this compound. And finally, these two are the same. And the third compound I could get would be this. Now, this is ortho, this is para, this is meta. And the question is, what do you get? Well, it turns out organic chemists found out, and we'll do a lab on this. Z is called the director. Remember, switch is off. And have you ever gone to some event like at Kane County or DuPage County or wherever, and they have a thing where they made an open field into a parking lot? They have those people who do not like me, and I don't like them that much. They tell you, no, don't park here. Go all the way down there, park there, park there. And they're directing you where to park. I don't like that. Them, they don't like me because I don't listen. I park close to the door. But anyways, I don't go to those places anymore. Those are directors. Now the Z group on there is a director. It tells the incoming, in this case, halogen, where to go, which carbon or carbons. Now, we'll have a lab on that, but since I found out the first day that those of you showed up were not going to be becoming organic chemists, I would rather spend more time on things that would be important to you the rest of your life than what type of directors there are. And how does that work? We could spend a week or more. I'd rather do that on proteins, carbohydrates, or fats and oils, things you might use the rest of your life. So I'm not going to cover directors in here. But just a quick thing, there are two types of directors. One is called an ortho-para director, and the other is a meta director. And depending on what Z is, and we use the term electron withdrawing or electron releasing, you get either this type of products, a mixture, or this one. And we're going to do a lab where you'll learn a little about it. But remember, what we do in the lab, I never ever put on a lecture test. And the only thing on the lecture exams are things I talk about in the lecture portion. So what that means in the long run is this reaction with chlorine and this one with bromine are the only two I can ask on an exam, because we're not going to deal with directors. let's look at the next reaction. That's called nitration. There you take a benzene ring, react it with HNO3, that's nitric acid. You react it also at the same time with sulfuric acid, H2SO4, and that puts a nitro group on there. And with that, that's the only reaction I can ask on a test because I'm not going to cover directors. But let me show you something that won't be on the test, but it'll help you understand what's going on here. Now, what happens is, think of nitric acid with this structure, H and 3 oxygens. Now, sulfuric acid is an acid and it is a proton donor. And the oxygens here, oxygen electrons attracts that. Again, this won't be on a test, to form this. Does anybody see something in there that looks stable? And the answer is this. What's 2 hydrogens and oxygen? 2 hydrogens and H2O, water. And what happens is, whenever you form a good leaving group in a molecule, it says, goodbye, I'm out of here, and you lose water. And what are you left with? Oh, by the way, this has a plus charge. And this is called the nitronium ion or cation. And this thing wants electrons in the worst way. And it reacts, and that's why you get NO2. Now, the hydrogen that was on here comes off as plus H plus, and you get back your catalyst that went here. And that's what a catalyst is, something that doesn't react. So that's how you have it. And the only thing I can put on a test besides this would be the following. Remember, on test 1, I'll just have, of all the general reactions, this one synthesis. And the question would be, what's the starting material for this reaction? And if we look at what's the general reaction, this reacts with what? Benzene ring. And that would be your answer right there. Don't forget the bonds. If you were to put this or a circle, that's cyclohexane. That's not benzene. So be sure to put that in there. Why I'm telling you that, it's happened more than once. I've had a student lose a lot of points on a test because they forgot to put that in there, which I don't like seeing them lose it, but it's wrong, it's wrong. So this is nitration, and we'll do a lab on this, in fact, Wednesday. Now, next one is sulfonation. And sulfonation, similar type chemistry, you react SO3, sulfur trioxide, sulfuric acid, and you put on the sulfonate group on a benzene ring. Remember, it's SO3H. You put SO3, forget the H, I marked that wrong, because that's important. The SO3 doesn't exist. It also has to have the hydrogen. And this is important because this is an important reaction to help make your laundry detergent key ingredient, the actual molecule that gets the dirt and grease off your clothes when you do the laundry. If you're the one who does the laundry, I do, I live alone. Now, it's time for something very special. That very special thing is, in this class, and a number of years ago, I had more than one student count how many general reactions I taught during the semester. And they came up with, I think it was 52 or 53, I don't know. That's how many I'll teach you this semester. Now, I know about 400 general reactions, which means I'm not teaching you all the reactions in organic chemistry, general ones, but of all the ones I know, there are only a handful, very small number, under 20, of reactions that you make a carbon-carbon single bond. That's something very rare, very special, and very fun, and a lot really important to do. So whenever you can make a carbon-carbon single bond, that's something special. You see my ears picked up like that? Oh, it's that awful. Remind me, never ever do that again. That was the first and last time. Sorry. Anyways, bad Tuesday humor. Now, another thing I should tell you, it hasn't been done that much in the last 20, 30 years, but for many, many decades, if you were to discover or create a new chemical reaction, general reaction, your name was associated, because that way you were honored for doing something really important in organic chemistry. So what does that bring us to? The next reaction. And that's Friedel-Crafts alkylation. Now, the two chemists who worked together to discover this were Friedel and Crafts, which I believe they're English organic chemists. Alkylation means putting an alkyl group, an R group on a benzene ring. And Friedel-Crafts alkylation, you start with a benzene ring and you react it with an alkyl halide. Now, R is anything with carbons, X is a halogen for this one. They usually only use chlorine or bromine, and you need a catalyst, which they found worked quite well, aluminum trihalide. And this puts an R group that comes from the alkyl halide on a benzene ring. You also get HX, but this is inorganic, so you can go, I don't need to know that. But some people like to, so that's why I put it down. And the carbon with the halogen is the carbon bond to the benzene ring. The carbon with the halogen is the carbon bonded to the benzene ring in the R group. And this allows you to make that very special, wonderful thing, a carbon-carbon single bond. And sometimes I'll put this over the arrow, this one. And the question is, what would be the organic product or product for the following? And we look here and say, what's different? Ooh, a benzene ring. That's different. I'm reacting, what's this? Carbon, carbon, hydrogen, carbon, carbon. Ooh, a halogen. So this is an alkyl halide. Remember, R means anything with carbons or hydrogens, and halogen. And this would be my R group. And I have aluminum trichloride, which I can abbreviate aluminum trihalide, where X in this case is chlorine, or it could be bromine. And you replace one of the hydrogens with the R group. And the carbon with the halogen is the carbon that the benzene ring is bonded to. So if we look here, I have my benzene ring. Do you break carbon-carbon single bonds? No. So I have 1, 2, 3, 4 carbons. Which carbon in R is the halogen bonded to? The end one, this one right here. And that's going to be the carbon the bonded to now the benzene ring. 1, and we have 3 more attached to it. Benzene counts as one bond. So, and there you go. And that's how you do Friedel-Crafts alkylation. Now, let me show you one other aspect of this, or better, yeah, let me show it to you. And what do we have here? A benzene ring plus, carbon, halogen carbons, Rx. I have right here aluminum trihalide, and X can be chlorine, or in this case, bromine. And you replace one of the hydrogens and make that very special, very unique, very great thing, a carbon-carbon single bond. Now, here's my R group. The carbon's attached to the halogen. So I'm gonna have a benzene ring. It's got 4 carbons, my R group, but which carbon has the halogen? Don't forget this, Dr. White, I didn't. The second carbon, remember the bond from the benzene ring to R goes to the carbon in the R group that's bonded to the halogen. In this case, carbon number 2. You don't break carbon-carbon single bonds. And notice when the halogen is on a different carbon from the end, you get the benzene ring bond to a different carbon. Here it's to the end one because the halogen's on the end. Here's this one because the halogen is on there. And it's your turn. What would be the product or products for the following reaction? 3 points each. In other words, give the organic product or products. And when you're done, give me a thumbs up. All right, I think everybody's done. So let's do this. What's different? A benzene ring. Carbon, carbon, carbon. Look for what's not carbon, what's not hydrogen. A halogen. Alkyl halide. RX, that's what it's called. And we have aluminum trihalide catalyst. And this is, remember, X can be chlorine or bromine. And the answer is you make a carbon-carbon single bond, make an alkylate, or put an R group on a benzene ring. What's my R group? What carbon has the halogen? The N one. You break carbon-carbon single bonds? No, so I start with 3. I better end up with 3. And if it was on a different carbon, like the center one, that would be wrong. And that's like, oh, I got to do another one. And why don't you try this one? What would be the product or products for the following reaction? I'm working you hard today. You're doing organic chemistry. Hopefully it's not that painful. All right, I think everybody's done. Are you all done? Oh, nobody's screaming at me, stop. So let's do this reaction. We come here, what's different? Ooh, a benzene ring. What's different here? We got a ring, but a ring is this carbon-carbon single bonds, carbon hydrogen, but wait, we have a halogen on that ring. So this is R, and the halogen is X. And notice we have this catalyst, aluminum trihalide, and X can be chlorine or bromine. In this case, it's bromine. And you make that very special thing, a carbon-carbon single bond to the benzene ring. Now, what's my R group? A cyclopentane ring. So I have benzene, and then I have my ring. And that's how you do it. Are you going to put it on any carbon? I guess it would have been easier for most of you to draw it like this. But all I've done is rotate it 2 times 360 divided by 5 degrees, but any carbon with the cyclopentane ring. Now, on test number 1, I'll just have one synthesis. Ooh, this is 2 molecules reacting with aluminum trichloride. To make this molecule. So it's your turn. What would be the 2 starting materials? That's why I have 2 question marks. When I was a student, our instructor didn't be nice like this. You had to figure out there were 2 things there, but I'm going to help you out. Don't tell anybody I'm being nice. I'll ruin my image around here. Shh. Hint, hint, hint. When you're done, give me a thumbs up. I see 2 people have already done that. And I see the other 2, so I better get to work. You're not going to be happy with me. I wouldn't want that. Now, how do we do this? We look at what's different. Here's our product. Oh, I got a benzene ring. That's different. What's on my benzene ring? This. And that's carbons and hydrogens. And I'll use the R group just like math uses X and Y. And I'm reacting with aluminum trihalide. And what do you react? Benzene ring plus Rx. Now, if I come up here, one of the question marks, it doesn't matter if which one you put first or second, has a benzene ring on it. Now, the second one, notice the R group here is 3 carbons. So I'm going to start with 3 carbons because I'm not putting any more carbons in, and you can't make them out of thin air. If you find a way to do that, let me know. We'll be rich. No, you can't. Now, alkylation, Friedel-Crafts alkylation. I honor the memory of, I don't know if they're still alive, Friedels and Crafts, but I honor their great work. The R group that's here, the halogen, is on the carbon in R that this bond is to, which is the center carbon. So that means the center carbon has the halogen. Where do we find that? Remember, X can be chlorine or bromine. And it's chlorine, and it's on the center carbon. And now I can put it in my hydrogens. And that's how you do it. And that's the fun and the beauty of synthesis. You learn how to make new molecules. And that's how you do it. Any questions on that? And that's Friedel-Crafts alkylation. All right, let's talk about now an important area in aromatic compounds, and that's polycyclic aromatic hydrocarbons. What does that mean? Oh, poly. For those who don't know, and I'll use it again in chemistry and other ways, poly means many. By the way, don't ever, ever, ever go up to a woman or a man. I think it's mainly women are called poly and say, your name, your name means many. There was a very fine woman, unfortunately, about a year ago, she passed away. She was from old age, whatever disease, I don't know she had, and her name was Polly Nash, very nice woman. And she used to be the Dean of English at Elgin Community College. And through friends, I got to meet her and her partner, and very nice lady. And the first time I met her, being a stupid organic chemist, not knowing, I said, do you know your name means Medi in organic chemistry? Polly? And she gave me that look like, how many times, a million times do you think I heard that? And I apologize because she probably heard it a million times, but poly means many. So polyaromatic hydrocarbon, polycyclic, cyclic means ring, many ring, aromatic hydrocarbons. Now I stayed away from polycyclic alkanes, they exist too, and that's where you have different rings. Now, before we go in there, let me show you. you can have what's called fused rings. Notice here, they're sharing two of the same carbons. They're fused together. This is ring 1 or 2, or you could count the other way. Now, it turns out you can have aromatic compounds that have polycyclic, many cyclic aromatic hydrocarbons, hydrocarbon molecule with only carbon and hydrogen atoms. That's an aromatic compound with more than one ring. And I won't ask on a test, but naphthalene is an example. And remember, aromatic number of pi electrons. This won't ever be on a test, what I'm showing you, 2n plus 2. And each double bond has 2 pi electrons, 2, 2, 2, 2, 2, 2, 4, 6, 8, 10. So 10, and when n is 4, that's true. So this is aromatic, and that's called naphthalene. That's the common name, which I don't know if that's the IUPAC name. And naphthalene has a very characteristic odor to it. If you know mothballs, because mothballs are just naphthalene pressed in little balls. And don't ask me why, because I'm an organic chemist. I know nothing about the insect world other than how to kill them with fly swatter or other things when they're bothering you. And that is, moths don't like the smell of that, so keeps them away. So that's a polycyclic aromatic compound. By the way, it switches in the off position for this next couple of pages, but I want to talk about it. Now, there's an interesting, I don't know if you call it compound, item that you can find, graphite. And graphite is this carbon in a special form, and there are large sheets of polycyclic aromatic compounds stuck together on top of each other. How many of you ever seen chicken wire or fencing where you see this? And so on, so on, so on. And that's the structure of graphite, or each sheet in graphite. How are we doing time-wise? You know something? Let's take a little longer break. I'm gonna give you an extra 30, 40 seconds. We'll come back to this because this will be a good time to take a break. Let's see. Come back at 2:50, and I'll see you in 5 minutes. I'm gonna go stretch, and we'll continue on. I'll see you in 5. Time to get back to work. All right. I don't know if I mentioned this or not. If I did, somebody gives me a thumbs up and say, you've already talked about this. That happens once in a while when you're teaching a couple of courses. You forget, did I do it or didn't I? Well, anyways, I'm going to show you something in Wikipedia. I used to say Wikipedia, but my students would yell out like Chem 170, it's Wikipedia. So they trained me how to say it right. Wikipedia has been, so I still like saying Wikipedia, but Wikipedia is so heavily policed in the chemistry by organic chemists like myself with the credentials that when I've requested a change, it gets changed because my credentials, that it's been a long time, many years since I've seen any major mistake in anything on Wikipedia in chemistry. Everything else I don't know about, but chemistry, it's been well policed. So let's look at Wikipedia for graphite. Now, graphite is this black material. Here's a picture of it. And if you rub your hands on it, you look at your hands and they'd be all black from the graphite. Now, graphite is a polyatomic, polycyclic aromatic compound. Yes. And does everybody see the little animation on your screen right now? Give me a thumbs up. All right, thank you, Joanna. Now, they don't show it, but think of each one of these as a benzene ring with its double bonds. And like sheets of a paper stacked together, one on top of each other, each sheet is stacked together to make graphite. Now, each sheet, and this is switches off on this right now, it won't be on test, but I think it's interesting, and you'll understand why this can play an important role in our life in coming years, already has started to. Each one is called graphene. Each sheet is called the sheet of graphene. Now, if you've ever written on a piece of paper like that with a mechanical or lead regular, I don't think I have a regular, oh wait, I think I do. Oh, a regular wood pencil. I don't have it sharpened, obviously. What's happening? Well, this has graphite in it and some clay to give it a little more strength. And when you're writing on there, the sheets of graphite come off in layers onto paper. And that's how you write on paper. Now, for many years, chemists said it's impossible to isolate one sheet of graphene from graphite. You can't. And about, 10 years ago, give or take a year or two, these two physicists who actually were doing chemistry, did something very creative. It had been well known in crystallography, X-ray crystallography, how to get analytical method to learn about the structure of molecules and crystals, that to get a single sheet of crystals, you put a piece of Scotch tape on a crystal, carefully pull it off, dissolve the Scotch tape, and you can get a pure crystal. Well, they did that with graphene. They put Scotch tape on a piece of graphite and slowly picked it up and took one sheet off and dissolved that, the Scotch tape in a solution, a chemical that will dissolve it. And lo and behold, in that solution were floating around single sheets of graphene from the graphite. And they won the Nobel Prize for that. Now, why is that important? Turns out when you have benzene rings hooked together like that, they're very strong, but they're also very lightweight. So this gives a way of possibly making very strong, almost as strong as steel, very lightweight materials that can be used things like your car, a jet, a bicycle, and whatever to make something that's very lightweight and strong. Well, if you have a car or jet that's a lot lighter weight, your gas mileage improves dramatically. Now, before they discovered that, something else was discovered about 93, 94, 1993, 94, and that's nanotubes. And these are large tubes of polycyclic aromatic carbon, 6-membered rings. It can't be made in real large quantity, like tons so far. But what's a nanotube? Let's see something. And here, if you take a sheet of graphene, can everybody see that animation? You can make a tube. And turns out Smalley of either Rice or University of Texas, I can't remember, let's see if I can find it. No, I can't. They found a way chemically with graphite and other things by adding certain strong chemicals, you can have a sheet rip off and form a tube like this. And these tubes are very strong and have the strength of steel, but the weight of super light plastic. And with nanotubes and later on with graphene, since about 95, 96, United States, Germany, Russia, Japan, China, each year they've been pumping in billions of dollars in the case of the United States into nanotube and nanoparticle. Nano is a billionth, meaning very tiny, but there are these tubes that can be used to make things that are very, very strong. And in coming years, that's going to be the way you'll see airplanes and other things made out of nanotubes. And that's all polycyclic aromatic compounds. Oh no, look at, guess what time it is? We've made it to, hold on, we've made it to the end of the chapter. You know what time it is, everybody? No, it's not time to leave, not yet. It's new chapter and new functional group time. And we're going to get into it. Now, if you look at the syllabus, it says alkyl halides. And I'm not going to do a separate chapter on alkyl halides, even though your book has it, because we'll encounter it like we just did in Friedel-Crafts alkylation. We'll have alkyl halides in other chapters too. So we're going to go into a new functional group, new chapter time. Well, if we're going to do that, I better close this chapter. And open our new chapter. All right, thumbs up, people. Do you see on there chapter 7, alcohols, phenols, and thiols? All right, coming attraction for this chapter. I'm going to talk about things that if you drink too much of it, which you shouldn't, especially if you're underage, you will get inebriated. I'll also talk about things that make your lips tingle and keep your lips nice and healthy. And I will also talk about stuff that stinks. I mean, stinks, real stinky stuff. And then I have a very sad story to talk about that happened back about 1937 involving organic chemistry. And because of that sad story, something good did come out of it that keeps us all safe and alive. So there's a lot of things to talk about. Let's talk about alcohols. Now, alcohols have the general formula ROH. R, anything with carbon and hydrogens, OH, hydroxyl group. A carbon with a hydroxyl group is an alcohol. Now, you've heard of alcohol, and I'll talk more about it, like in spirits, hard spirits such as vodka, my favorite, and also Canadian Club. That was my father's favorite, and I like it too. And also other types of alcohols. And all of them have in common, they have a hydroxyl group, OH, on a carbon. Now, what we'll do is I'll talk about nomenclature, then we'll do where you find it in the real world after we do nomenclature, and then we'll talk about how do you make alcohols, and then how do you react to alcohols. Now, a couple important things. One, test number 1 will cover alkanes, cycloalkanes. It will cover alkenes, alkynes. I'll be putting out probably tomorrow, what's today? Tuesday, today or tomorrow, a breakdown of what chapters and important information about test number 1. I believe test number 1 is a week from this Thursday. Because of the summer pace, and also I want to give you time to learn, we'll cover new material before we have the test on the material we've already covered. But it works well. At first it seems awkward, but it's worked well. I've been doing this in the summer for years. We finished the aromatic chapter, aromatic compounds. And that means this Thursday, I will go through the aromatic problem set. This Thursday, I'll go through the aromatic problem set. Remember, this is summer. In 1 week in the summer, we covered 2 weeks, so it's a faster pace. Please keep up. I try and finish early enough to give you time. And the answer is yes. Part of the day, I will lecture. What I will do in this class is all the tests are on Thursday. Why? Because I don't believe in multiple choice. I don't know if I told you this or not. I teach by my golden rule of teaching. And that is, I never do unto my students what I didn't like done to me. And I hated as a student multiple choice questions. Multiple choice questions are designed to trick you. They're not designed to say, here's a question, show me you learned the material. No, I'm going to trick you and see if you learned the material. And at the same time, are you going to fall for the trick I'm going to make you put the wrong answer down? And I don't like that. Never did as a student, don't like as a teacher. But what that means is there's no Scantron because I don't use multiple choice. So that means when I do a test, it's going to take me a couple hours to grade it for this class. So that's about my test. And what we'll do is on a Thursday, actually Wednesday before each test, sometime in the afternoon, I'll post the test in the assignment area of D2L. It'll be as a PDF file, but it will be password protected. Then on that Thursday, which will have lecture, after lecture, what I'll do is right 5-10 minutes after lecture, I will send you an email, each person with a password to open that PDF file. And you'll take the test and you'll have until Friday, usually 10 a.m. to take the test. You should only take about an hour or so. Uh, my test in organic, if you don't know the material, you could have all day and it's not going to help you. But generally, the way I write tests is like if we were face to face, you will finish. You should be able, most students finish. If you have 50 minutes, they're usually done in 35, 40 minutes the latest. As I write a test, again, my golden rule, I never liked the test where most of the class couldn't finish. In science and math, yeah, I would, but rest of the class wouldn't. And other things, well, by the way, if I haven't told you, in grade school, I was always the first one down in spelling bee, always. Other stuff, I won, spelling. But anyways, so you'll have enough time, and then you'll create a PDF file, either with a scanner, or as you've seen with the lab, you can use your cell phone to create a PDF file, have instructions, and you'll upload it to the assignment area. So you'll have from the end of class Thursday till 10 o'clock Friday morning. I think that's enough for everybody to find room, whether you're working a certain shift, to be able to take the test. Like I said, the test should not take you more than an hour, shouldn't take you more than 40, 45 minutes, but take an hour and then the extra time to make the PDF file and upload it. And this is how I give tests. Does that answer whoever, let's see, who asked that question? Natalie, did that answer your question? You're welcome. And if, like I say, all questions are good questions. You know, you're here to learn. I'm here to help you learn. And also, part of my job is to evaluate that you've learned the material. And that's my test. And my test, you'll find out after test number 1 why I call them practice problems. Wink, wink, hint, hint, say no more. I stole that from Monty Python. If you've never seen Monty Python Flying Circus skits or the whole show, which was on in the late 1970s on here at WTTW, because it's an English group, you're missing some of the best comedy that's ever been created on TV or in the movies even. They did the Monty Python and the Holy Grail. That's an awesome movie. On par with Blazing Saddles. If you never saw Blazing Saddles, you should. All right, let's talk about alcohols. Well, I better write an alcohol on the screen. And this material, alcohols, and what I'll be covering now next, later this week, will not be on test number 1. It'll be on test number 2. Now, look at a molecule. Look for what's different. Oh, an oxygen with a hydrogen. It's the hydroxyl group on a carbon. And what do we call that? An alcohol. So hydroxyl group, OH, on a carbon is an alcohol. Now, how do you name alcohols? The hydroxyl group OH in alcohol is indicated by changing the ANE ending of the longest carbon chain containing the carbon with the hydroxyl group to OL ending. Then you need to use a number if it's here. I should have added if it's acyclic, what what carbon it's on. And the rest of the IUPAC rules follow, except the hydroxyl group has highest priority in the numbering system. It's getting the lowest number. What does that mean? Well, let's take a look at our example. We have a hydroxyl group on this carbon. How many carbons along this chain? 1, 2, 3, 4. That's butane. Now you understand why I asked you to learn that chart. Now, for an alcohol, the ANE ending, you drop the E and add OL. OL ending, alcohol. And for acyclic, you need a number. And the number is what carbon? First of all, alcohol, drop the E, add OL, butanol. What carbon is it on to give it the lowest number? If we start this way, it's on carbon 2. If we start this way, 1, 2, 3, it would be on carbon 3, which is lower number, 2 or 3. I hope you all agree, 2. And I'm done. That's 2-butanol. Oh, let's do another one. And if we look at this molecule, I'll do one, then I'm going to let you try one on your own too. I'm going to let you have fun too. We say, what's different? What's not a carbon-carbon single bond or carbon or hydrogen? Oh, oxygen with a hydrogen. Hydroxyl group on a carbon. Hydroxyl group on a carbon. That's an alcohol. And what's the longest chain? 1, 2, 3, 4, 5, 6, 7, 8. And it's got to include the carbon with the hydroxyl group, or 1, 2, 3, 4, 5. Which is a greater number? Hopefully I'll pick 8. That's octane. But alcohol, find a name, the alkane, drop the E, add OL, octanol. Which carbon is the hydroxyl group on? 1, 2, 3. Went the other way, it'd be 1, 2, 3, 4, 5, 6. So it's 3, and this is a C, octanol. Are we done? No. As soon as we say that, that's spoken for. Oh, look, it's your old friend, the methyl group. And this is carbon 3, it's on carbon 4, so that'd be 4-methyl 3-octanol. That L looks awful. Let me fix it up. So 4-methyl 3-octanol. And that's how you do it. Let's look how we did it. We found the longest chain with the carbon with the hydroxyl group, because that's what an alcohol is. Remember, look for what's different. What's not carbon or hydrogen is where the fun is. Gets your attention like that. And the hydroxyl group is on this carbon, alcohol. What's the longest chain? 8, octane, alcohol. Drop the E, add OL. OL ending is an alcohol ending, tells you an alcohol. And what carbon has the hydroxyl group for acyclic? The lowest carbon nearest to the end of the chain. Remember, you always start numbering at the end. Some students would say, oh, that's carbon 1. No, it's carbon 3. And so that's 3-octanol. I circle as soon as we say 3-octanol, what's spoken for. And then it's your old friend, the methyl group. that's on carbon number 4. And here's one for you to try. Give the IUPAC name for the following. And remember, IUPAC means the official name, even though I like to say it stands for International Union of Pure Applied Chemistry, which it does. Well, I think everybody's done. Looks like we lost a few people, but this is an internet course, and I'll move on. All right, how do you name this compound? Look for what's different. What's not carbon, what's not oxygen, what's not a carbon-carbon single bond. Oh, oxygen with a hydrogen on a carbon. Alcohol. And for acyclic, find the longest chain with the carbon with the hydroxyl group, name it as an alkane, drop the E, add OL plus a number. So if we look over here, we have 1, 2, 3, then that'd be 4, 5, but here we have 4, 5, 6, 7. So the longest chain is 7. That's heptane. Drop the E, add OL, heptanol. What carbon is the lowest number? The carbon with the hydroxyl group. Here it's 2. We started from here, it'd be 1, 2, 3, 4, 5, 6. Which is lower, 2 or 6? Hopefully I'll pick 2. So it's 2-heptanol. As soon as I say that, that's all spoken for. Oh, look, we have something left over. 2 carbons, alkyl group is ethyl. What carbon are they on? If this is 2, this has to be 3. So that's 3-ethyl 2-heptanol. And that's how you do alcohol nomenclature. Well, let's do, before we do rings, now, when either carbon could have the hydroxyl group and it doesn't matter because it'd be the same, you don't use a number. And let's look at this molecule. What do we have? Hydroxyl group on a carbon, alcohol. And you find the longest chain, name it as an alkane, drop the E, add OL. And here we have 2 carbons, ethane, drop the E, add OL, ethanol. Now there's no number because you can't have a 2-ethanol. If this is carbon 1, if I put it on this side, that would still be carbon 1. so you don't have a number. Now, let's take a look at this little molecule here. I'll draw it again. And this is a very interesting molecule, ethanol. That's the molecule that gives beer, wine, carbonated alcoholic beverages like champagne and sparkling wine, and hard spirits like vodka, Canadian Club, the good stuff. The kick it has, in other words, it's the molecule that gets you inebriated when you consume, which I'm not in any way advocating, too much of any of the aforementioned things like vodka. Have you figured out what my favorite one is? And how that molecule does that, I have no idea, but it does. But while we're talking about ethanol, next time you go into a gas station, you'll see by the pump, either there's a black sign with white letters or a white sign with black letters that says in Northern Illinois, most of the United States, I think, if not all of it, this gasoline contains up to 10% ethanol. First of all, don't ever drink gasoline. It'll be serious harm to your body. But they put the ethanol in there to help your engine run better. And next time you're with friends, you can show them that and say, oh, look, there's the IUPAC name for an alcohol that's in gasoline. Don't, you'll lose a lot of friends. Now, what about rings? And I don't have a slide for it. Cyclic alcohols. If we look at this one, what's different? Ooh, I got a hydrox group on a carbon, but I have a ring. Well, how do you name this? Remember, this is an alcohol. You name this case, the ring is a cycloalkane, drop the E, replace it with OL, but you never use a number. When it's the only functional group in a molecule, which in my class that will be true. And therefore, because that carbon is always number one, everybody knows that, so you don't need it. This is a 5-member ring, cyclopentane. It's an alcohol, so I'll drop the E at OL, and that's cyclopentanol, and I'm done. And how would you do this one? Let me do it, and then I'll give you some to practice. I say, what's different? Ooh, hydrox group on a carbon. This is an alcohol. It's a cyclic alcohol. So name this cycloalkane is attached to it. Drop the E, add OL, no number, but the carbon with the hydrox group is always number one. So 6 carbons, cyclohexane. It's an alcohol, so I use the OL ending. This carbon is 1, but everybody knows that. Then the alkyl groups you number in such a way, clockwise or counterclockwise, that they also have the lowest number. So this would be 2, 3 carbons, N carbon is N-propyl. And this would be 2N-propyl cyclohexanol. And that's how you do it. So I better give you some to try. Why don't you try this one? Give the organic, wrong problem. It's been a long day. Give the IUPAC name for the following molecule. And when you're done, give me a thumbs up. I see one person is done. There are only two. Everybody's done. I better get ahead. All right, what's different? Hydrox group on a ring, 5 carbons, cyclopentane, but it's an alcohol. Let me just move a wire that's in my way on my writing tablet. It's an alcohol. Remember AN ending, just drop the E, replace it with OL. That's the alcohol ending. This carbon is 1. Oh, it's our old friend, the methyl group. And this is 1, 2, 3. I went the other way, 2, 3, 4. 3 is the smaller number, so it's 3-methyl cyclopentanol. Oh, let's do another one. Oh, let me give you an interesting one to do. Oh, that's a pretty molecule. And the question would be, give the IUPAC name for the following molecule. 3 points each. And a quick commercial from Dr. White. I'll send out an email too, but remember the lab we did yesterday is due tomorrow. You should upload it to the assignment area of D2L. All right, everybody's done. I better get to work. Now, if we look at this molecule, we say what's different, what's not carbon, what's not hydrogen, oxygen. And so OH group on a carbon of the ring, alcohol. Name the ring as a cycloalkane. Replace it with an OL, excuse me, when we drop the E. And the carbon with the hydroxyl group in a ring is always number 1. We don't show that. So how many carbons in that ring? 6. And that would be cyclohexane, but it's an alcohol. Drop the E, add OL. And then what do I have there? I have a methyl group. Oh, my favorite, and I'm going to start calling it, because I'm a lazy organic chemist, a T-butyl group. And if this is carbon 1, this is 2, 3, 4. So we have 4 T-butyl, 1 methyl, and a 5th cyclohexanol. Now, for this class, if you would put the 1 methyl first and the 4 T-butyl second, I'd still give you full credit. And that's how you do it. Now, there are two types of nomenclature questions. Here, give the name. Here's the structure, give the name. The other is, here's the name, give the structure. And I'll do this one. How do you decode this? And the question would be, draw the structure for the following, or just for. And how do you decode this? Always start from the right, move left. OL ending. If I can spell it. Alcohol. And what, if this were an E, 5 carbons pentane, so I have 5 carbons. Where's the alcohol? On carbon 2. Now I have to tell you something personal. When I learned this as an undergrad, the instructor I took, and even when I got the grad student, all my advisor and other organic chemists at Michigan State, always with alcohols started on this end as 1, on the right, not the left. And good habits, Dr. White doesn't break. So I'm going to call this 1, this 2. Now you could go the other way. I still mark it correct, but I like doing it this way because that's how I learned. And it's got a hydroxyl group. Then we go over here. Oh, I know methyl, CH3. It's on carbon 3. So that would be this carbon. And then you know there are 4, yes, 4. Just 4 bonds to carbon, so I can put in the rest of the hydrogens. Just think, 4 weeks ago, you didn't know that. Now you know that quite well, and that's how you do it. Again, start from the right, move to the left. OL ending, alcohol. If this were an E, pentane, 5 carbons, what carbon has the hydroxyl group? Number here tells you carbon 2, then a methyl group on carbon 3. Now, I'm going to do this, it's going to be real rare, so be sure to write in your diary, dear diary, Dr. White started an alcohol counting from the left. Now, this would be perfectly correct. Let's call this A and B. Those are really the same molecule. All you've done is rotated 180 degrees. Rotated 180 degrees. On a test, which is correct, A or B? And the answer is both, because Dr. White, me, has a piece of paper signed by the Board of Regents of Michigan State University saying, I know those are the same, otherwise known as my PhD degree in organic chemistry, synthetic organic chemistry. So again, that's how you do this. So I'm going to have you try one. And why don't you try this one, 3-T-butyl, 1-decanol. Please draw the structure. And this may take a while because there are a lot of carbons to draw. And we'll wait until Joanna is finished putting the pressure on her. No. All right. How do you decode this? You start from the right and move left. OL ending, alcohol. If this were an E, decane, 10 carbons. I better get to work. Let's see, 1, 2, 3. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Success. Now, it's an alcohol. Which carbon has the hydroxyl group? The N carbon, 1. Now, you could have put it on this one, but I'm going to do mine, like I said, on the right. Then I'll move 3 over, 2, 3, and I have a T-butyl. Dr. White loves T-butyl groups. And now it's time to put in the hydrogens. Remember, there's 4 bonds to carbon. And we're done. Let's look at this. Decane, 10 carbons across. On carbon 1 is the alcohol, 1 decanol. And on carbon 3, there's the T-butyl group. Oops, forgot to do those. Oh, I forgot. You guys should have caught that. Well, luckily I did. And that's how you do it. If I look at the clock, oh my goodness. Time flies when you're having fun with organic chemistry and Dr. White. Now, let me remind you, don't forget, tomorrow is the lab day. Monday and Wednesdays are lab days. The lab we did on Monday is due tomorrow. Just about everybody did that. I'm going to be working later today, grading your labs, and I'll post those scores in D2L. And also I'll talk about on probably Wednesday about grading, and if you ever have any questions about grading, which you can ask. And so don't forget, the lab is due tomorrow. On Thursday, we will go through the aromatic problem set. With that, I'm going to say, gain gesund, be healthy. Bye.